শুরু করুন।
Good morning, everybody. Sorry for the delay. The program has to be live streamed, and the live streaming link has to be uploaded in the AICT portal. So that's the small activity that we are doing. So it will take around 2-3 minutes. Please have patience. Live streaming AICT अपलोड করে দিয়ে আসছে রান টাইমে ওরা যেটা দেখতে পাচ্ছে প্রচুর ঝামেলা ভিডিও
Good morning, everybody. I'd like to invite, on behalf of Department of Mechanical Engineering, Healthy and Safe Technology, to all the dignitaries and participants to AICT Atal sponsored faculty development program titled Innovative Micro and Nanotechnologies and Fundamental Applications. So, as we know, the micro and nanotechnology is an emerging area. We have already midway through it in the faculty development program. We had the online version last week where eminent speakers deliberated about different topics which were enriching. Here we again back with the offline mode of the same faculty development program. So I'd like to begin the program with national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे शुभ आशीष मांगे गाहे तब जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे।
Now, all the dignitaries will be welcomed with bouquet and dorio. So, in this regard, I first like to ask our Associate Professor Dr. Abhishek Shamanto to felicitate Principal Health and Safe Technology Professor Shubhrata Kumar Mundu. Next, I'd like to invite Dr. Devashish Dashvidari, Associate Professor, Department of Mechanical Engineering, to felicitate Dean of Engineering, Health and Technology, Professor Tobun Kandija. Next, I'd like to ask Dr. Shubhriya Roy, Associate Professor, Mechanical Engineering, to felicitate today's eminent speaker, Professor Shondip Sharkar. Last but not the least, I again like to invite Dr. Abhishek Shamanto, Associate Professor, Department of Mechanical Engineering, to felicitate Head of the Department, Mechanical Engineering, Professor Gautam Kumar. going forward, I'd like to invite Principal Health and Technology, Professor Shubrat Kumar Mundu, to say a few words.
Good morning, everybody. Respected my dear colleagues and students and other dignitaries coming from other institutes or organizations. It's a great pleasure to me to be present here to inaugurate these functions with you, and I am also happy to say something. Although I am not a good orator, I'll try to say something about the faculty development program. Actually, faculty development program is very much important to each and every institute, and it should be organized in a systematic manner, because faculties does not lack their teaching style, and they are not only that, they should be cautious and responsible that the upgraded and updated the knowledge where they can deliver to their students to make their perfect, and the students can take the challenge in this global marketing, the existing global market. So, faculty development program, it has some benefits. Suppose the participant will get the opportunity to ask the questions, to share their knowledge, to set up their motto, long term or short term, and the outsider who are here, you should know that the Holy Technology is a very good dynamic college where each and every faculty always try to learn their students at the best level. So I expect that every participant will gather some knowledge and they will enrich their knowledge, which deliver to their students for the benefit of the nations. So with these few words, and I wish that every success of this program, and thanks to the participants for their sincere presence. With these few words, thank you all.
Thank you, Principal Sir, for his kind words. Now I'd like to invite Dean of Engineering, Health and Technology, Dr. Tarun Kantijagan, to say a few words about the FTP.
Good morning, respected principal, also he has just left, distinguished guest and today's speaker, Professor Sandeep Sarkar from Jadavpur University Mechanical Engineering Department, the two organizers, coordinator, Professor Gautam Bose, HOD of Mechanical Engineering, co-coordinator Dr. Abhishek Samanto, other faculty members, participants from academia, industries, and students. You know that currently we are living in the 21st century, and the society, the industry, the business, the academia, all sphere of life is undergoing unprecedented competition, particularly thanks to the proliferation of information technology, computer, internet. So these are the very buzzword and highly prolific areas. So this advanced automation, advanced computation, communication, these are essential to combat the unforeseen challenges that we are facing in the 21st century. If you go to your internet, mobile, you'll find several development related activities or phenomena will appear. But at the same time, it is also of immense importance that we have to focus our attention to the simultaneously to the devices, to the different processes and different physical phenomena. In this context, this 2 weeks FTP program, which is organized by the Mechanical Engineering Department of HIT under ATOL AICT scheme, is really wonderful. This innovation in the micro and nano-technologies also should go hand in hand with the development of the computer communication and other devices. So this 2 weeks program, where first week is already covered up in the online mode, and in this particular week, this will be pursued and executed in the physical mode. Quite a good number of reputed faculty members from the IITs, NITs, Jadavpur University, they will deliver their speech, they will share their experience in these promising areas, and I believe that all the participants and other members who are associated with these particular programs will be immensely benefited. And I also think and I also feel that these discussions will have an immense impact in our coming days research work and even in the industrial activities. So I would suggest on this particular platform that even after completion of this FDP program, you please pursue or identify the relevant areas that will be discussed over here, and you can apply in your different work domain or in the research or academic activities. So I wish all success to this particular FDP program which will be pursued in this particular week in the physical mode. I wish all success, and I also believe that you will enjoy the delivery of the different eminent faculty members all over our country. I wish all the best to you. Thank you.
Thank you, sir, for sharing your thoughts. Now I'd like to invite Professor Shondip Sharkar, Professor in the Department of Mechanical Engineering, Jadavpur University, to say a few words about the FDP.
Very good morning to Dean of Engineering and HOD of Mechanical Engineering and my colleagues from different engineering colleges. It's a great pleasure for me to be here and deliver a talk on innovative micro and nano-technologies and fundamental principles. So during this course of during the course of my lecture, we shall be interacting on different areas of micro and nanofluidics where we can apply our fundamental knowledge, fundamental concepts in the development of different nanotechnology devices. And definitely my talk is restricted to basic on theoretical basis. So how we can apply our theoretical knowledge for the design of optimum sensors, macrofluidic sensors, those stuff we shall be discussing. I am restricting my this lecture in a short period of time because anyway we shall be interacting more during our interactive session, forthcoming interactive session. And thank you all. Hopefully during my talk you shall be enjoying with the technology that shall be discussing primarily on theoretical perspective. Thank you very much.
Thank you, sir. Now I'd like to invite Head of the Department, Mechanical Engineering and Coordinator of this program, Professor Gautam Kumar Ghosh, to say a few words.
Good morning. Good morning to one and all. Respected Professor Dr. Subrata Mandal, our Principal Sir, Professor Dr. Tarun Kanti Jana, Dean, School of Engineering, Professor Dr. Shondip Sharkar Sir from Jadavpur University, my co-coordinator, Professor Dr. Abhishek Samanto, Shiru Banerjee, Supriyo Roy, all the faculty members of Mechanical Department and all the participants as well as the students who are helping us out. A very good morning to all. So I welcome you all to this 2-week long. First week was online, so from today onwards we'll be having offline faculty development program on micro and nanotechnologies. Obviously, the online evaluation has already been taken place, so I will not elaborate much. See, this nanotechnology, as you have been through 1 week long class, you find that the miniaturization of the material to its smallest extent, right? Like in micro nano, then we have this femto. So till the femto level people are working. Like one of our professor from IIT Madras, he has shown like the micro drilling holes from turbine blades at femto level through laser machining. So this kind of work are being conducted globally, and India is not far away. So the miniaturization of all the materials, be it an IC, be it a lab on chip, be it any electronic component. So we are having miniaturization of the components. So for that, the nanotechnology plays a pivotal role. Okay. So see, in nature also this is already there. Like a plant who is extracting the nutrient from the soil and taking up to say 12 feet, 14 feet or 20 feet. So that is also a nano or micro channel technology wherein the materials are being taken from far below, say 3 feet, 4 feet or maybe more. The nutrients are being pulled through the capillary action to the top of the plant. So that technology human still do not know how it is happening. Right. So we are only trying to mimic the nature, but we are falling far behind her. But the technology is already there in the nature. So we just need to understand and develop those ideas. The nanotechnology is one such area which will venture out into the various ways and means of making those particles, not only particles, how to channelize those particles through the miniature form of capillaries. Like nowadays, you will find the medical devices which are being used for examining various medical conditions of human. So these are basically small components like lab on chip, which actually helps for diagnosis. Now, targeted treatment on human are being taking place through different sensors or nanobots, which are given into the bloodstream to early detect of diseases or to monitor the human condition 24/7. So in the medical field also, this nanotechnology is playing a very good role in finding out the health condition or monitoring the health condition of human, and based on that the treatment can be given. Like nowadays, what doctors are going like they are trying to find out the affinity of medicine for a particular human being. Now, till now, what we do, like we give medicine based on generic assumption of a person. Like I have a fever, so they give me some kind of paracetamol. Whether my body have affinity towards paracetamol, then only it will work. So that health condition, particular medical affinity of a person has to be first evaluated, then a particular medicine has to be given. So this is the targeted medicinal approach which the medical world is now trying to portray. So for that, a lot of researches are going on and a lot of technologies have come up. Okay, now in our FDP, for the first week, it was a wide spectrum of speakers from every walks of engineering were there. From various institutes of national importance. Now this week also we have similar kind of blend and flavor, so that our emerging faculty members who are venturing out into the research arena can have some ideas and can get the impetus for research work and develop new ideas of research. So this kind of faculty development program will not only help in building the idea as well as evolving oneself from a domain, and the interaction between the various faculty members at one place will also help to figure out the future course of action. We are having a lot of participants from industry also. Well, that will also add on to the interaction. So I will not prolong much. So I welcome you again. I hope this week will be a very interesting one. So thank you. Have a nice day.
Okay, thank you, sir, for your kind words. Now, as we are running a bit late, so we'd like to directly go into the talk session where our Indian speaker will deliver his lecture. So, before starting, let me give a brief bio sketch of today's speaker. Today's speaker, Professor Sandip Sarkar, is presently serving as a professor of mechanical engineering in Jadavpur University, Kolkata. He did his bachelor degree from IIT Shivpur and master's degree from IIT Kanpur and obtained his PhD from IISc Bangalore. He obtained all these degrees in the discipline of mechanical engineering. He has more than 55 peer-reviewed research publications in various international journals of repute and several publications at international conference proceedings. Professor Sarkar also authored several book chapters published by various international publishing houses. He guided several master's theses and a doctoral thesis and presently also guided them. He has a few years of industrial R&D experience as well. Professor Sarkar's area of expertise is computational fluid dynamics and heat transfer, and also parallel in-house code development. His focus area is fluid structure interaction, microfluidics, nanofluidics, multiple flows, heat transfer, process modeling of steel making and casting. He has established a new self-funded microfluidic laboratory at the Department of Mechanical Engineering in Jadavpur University. Recently, he has also received GST and SM research grant for 3D parallel computations on fluid structure interaction research project. With this brief introduction, I'd like to invite Professor Sarkar to deliver his lecture.
Very good morning again, my colleagues. So let me start the topic that I have chosen for this faculty development program. Electromagnetic hydrodynamic control and energy conversion in a theoretical perspective. Again, I'm just reminding you again, I want the talk to be more interactive as possible. Please ask me, please stop me if you find anything difficult or you find that, just tell me that I couldn't understand this stuff. Why? Because here I just try to intend to incorporate a few topics that will be relevant for you for doing some theoretical or some theoretical perspective. Now in parallel, micro and nano devices are already explained by our by the HOD of mechanical engineering HIT. That in the microfluidics area, if you want to perform some research work or perform to analyze some given topics, you need research facilities in terms of experimental facilities, or you can perform the research or you can analyze certain topics of microfluidics and nanofluidics areas through some theoretical perspective, basic theoretical modeling. So theory you can analyze what is happening inside a macro. Now how we can optimize the different kind of situations if there is an interaction between the fluid and so why those things are required? Those things are primarily required for the development of smart sensors. Basically nowadays there has been a concept like lab on a chip, lab on a CD. Just pinching a drop of blood in a CD kind of device, you can you can diagnose what is happening and how the patient is affected with different kind of diseases. For example, nowadays recently COVID test protocol has been come. Just with a drop of blood a smart device, so that will generate some kind of, it will create some kind of signal. To the signal, you can also characterize what is happening, that whether the patient is affected with the COVID virus or COVID disease. So those tasks, if you analyze those tasks, you require certain understanding like how does this is understanding on transport phenomena, transport characteristics. Transport characteristics in terms of fluid motion, how the fluid is like the fluid motion is taking place, and whether you can control the fluid motion by the action of some external field. For example, here we try to understand if there is an external field in terms of electric field and combination electric field and magnetic field together. So the combined consequences with the electric field and the magnetic field, how we can control the movement of fluid flow inside the macro channel, and how we can optimize the heat transfer rate so that we can get some kind of indication whether we can design some kind of smart sensor that will be helpful for not only from the medical perspective, but also from, for example, high performance computing systems. Say nowadays, if you visit any like central government funded computing, nowadays it has come National Supercomputing Mission, NSM servers has come. At different IITs and also IISc, we have got different NSM servers, high performance computing servers. So maybe around 1,000 scores machines are those are coupled together with single LAN cable. When the machine is running at the full speed, at the high speed, it generates lots of heat. Suppose you are running your program, where you are running a computational program with millions and billions of or number of cells. There, what you have to do, you have to solve maybe more than maybe millions of linear algebraic equations. During the solution, the computer generates this, IC circuit generates this. Now, what you have to do? You have to remove the heat, right? If the heat is not properly removed, what will happen? We may have the fire incident, or at the same time, performance of the supercomputer will be reduced. So nowadays, if you compare your personal PC, desktop PC, we have SMPS fan, we have external cooling arrangement. But for the high performance system, like thousands of volts are coupled with a single LAN cable, external fan or SMPS fan may be very difficult. So only option would be the use of macro channels, macro channel cooling system. We call porous macro channel cooling system. We used to pass a very high coolant at a very high speed to a macro channel. It extracts the heat from the IC circuits, and accordingly it will generate some kind of external impedance to the circuit, which will reduce the heat. Those are the heating technologies, cooling technology that has come up. And another perspective is recently it has come paper-based macrofluidics. Then you may ask me that construction of macro channel is very costly because it requires special kind of arrangements, macro dealing, some those kind of stuff. But recently there is a recent development in macrofluidics area. We call it paper-based macrofluidics. Just a piece of paper. In a piece of paper, it will generate some kind of external PDMS coding. So it will generate a macro channel. Just maybe around 2 rupees, you can diagnose a disease. Just a few weeks back, one paper has been published recently that with dengue virus you can identify actual macro channel. Paper-based macrofluidics. Those are the typical applications, but you can find that macro channel or macrofluidics has got immune application, not only from the biological perspective, but also from the perspective of high performance cooling arrangement, all those kind of things. So here the objective is actually you are going to apply some external field in terms of magnetic field, and the magnetic field will generate some force. It will alter the fluid flow, and accordingly you can optimize the fluid flow. We call it electromagnetic hydrodynamics because macro channel has got some inbuilt properties of generating electric double layer. What is electric double layer? What is electromagnetic hydrodynamics? I will explain this to you. So here magnetic hydrodynamics, basically you are applying some magnetic field, and magnetic field will generate some current, and current will interact with the fluid flow, and it will control the fluid motion. Here, I think this stuff already you know, right? Magnetic hydrodynamics. What is magnetic hydrodynamics? For example, suppose you have a field, you are applying a magnetic field, and in any conducting material, if the fluid is conducting, what will happen? It will generate it will create or it will induce some electric current density. And the magnetic field, what you are applying, that magnetic field and electric current density will interact and it will generate a force. We call it impending force, and that force is we call it Lorentz force. So how it is working? For example, suppose there is a coil, and in the coil you are passing some current. So there is a coil, something like this, circular coil. You are passing some current to the coil. And now there are several laws: Gauss law, magnetism, Ampere's law, and Faraday's law. If you find the Ampere's law, the current, if you pass a current through a coil, and if you place some conducting material inside the circular path of the coil, it will create a magnetic field. It will induce a magnetic field. We call magnetic induction. And that induced magnetic field, it will interact with the current that you are passing through the coil. Okay, this kind of circular motion. You can see these are the different kind of motions, circular path motion I have shown here. And that magnetic field, say let us say B is the magnetic field which is induced due to the movement of the current through a coil. And there is B magnetic field, it will interact with the current density. Let us say current density is J. So J, the cross product between the magnetic field and the current density, it will create a force, it will induce a force, we call it Lorentz force. It will basically, you can see here, this is the Lorentz force, cross product between J and the magnetic field, Bj is the current density, B is the magnetic field, and that force, it will control the fluid motion. Now the properties of the force, how the force can be used for just maneuvering the fluid motion in the microchannel, it depends upon in which direction you are just passing the current. If it may be aided, or it may be it may suppress the fluid motion. So here the primary idea is that in this microchannel microfluidic applications, we may essentially apply this concept for maneuvering the fluid motion in a microchannel. That we shall see how we can apply this concept for maneuvering the fluid motion in a microchannel. So accordingly, I have shown here. There are several applications where you can apply the concept of magnetic field and electric field together, how they are interacting with each other, and in different industrial applications. So primarily whatever you are studying, that should have some industrial implication. Otherwise, it will be a completely theoretical application. So here you can see there are several industrial applications: electromagnetic studying, electromagnetic braking. So in steel industry, if you require certain kind of if you use the impurity in the steel, you may start the steel at a particular velocity. That is called electromagnetic studying. And also the primary main topic of our discussion is advanced energy efficient devices and sensors. That I was discussing that if you can apply the magnetic field for maneuvering the fluid motion, so you can basically get some optimum magnetic field for the fluid motion or fluid velocity maximum. So there you can augment the fluid motion in a macro form through the development of smart sensors. So you can apply some magnetic field in a different direction, which will basically create some fluid motion in a particular direction, or it may impede the fluid motion in a particular direction. So accordingly, you can develop the smart sensors and also separation of biological and chemical moieties. So in biomedical industries, for example, there is a concept called lab of the CD. In a CD, you are putting some droplet of blood or some samples. So there, how the sample or droplet will move in a particular direction, you can control the application to the application of magnetic field. That we call magnetophoresis or magnetohydrogen micropump. These are the typical devices that has been emerged so far through the application of magnetic field and electric field together. We call it magnetohydrogen micropump. The left figure here, this one, it was developed in around 2000 laboratory scale. There is a famous scientist, Zhang and Li, University of British Columbia. They developed this concept that through the application of magnetic field and combined consequences of electric field and magnetic field together, we can maneuver the fluid motion in a microchannel. Right? For example, if you consider how the fluid motion takes place when there is a conduit, right? Suppose there is a pipe and fluid is flowing through the pipe. So what is the driving force for the fluid motion? Pressure gradient. Right? If you have pressure gradient, then fluid will move. If you do not have the pressure gradient, fluid motion would be possible. That is called, by the application of electric field or by the application of magnetic field together, you can make the fluid flow inside a particular confinement. But there are certain considerations. Consideration with respect to the dimension of the channel that you are considering. Dimension of the application you are considering. Yes, please.
It has a magnetic property.
Yes, it has to be aqueous solution, which should have magnetic property. Because without magnetic conducting material, this concept is not valid. For example, if you add some sodium, like NaCl solution to the water, it will generate some magnetic property, or it may be electrically conducting, then it will generate magnetic property. Ionized solution also, correct. Absolutely right.
Sir, if I take alcoholic solution, then it will be.
If it generates ion, concentration of ions, then definitely some biological solutions. Definitely. Any questions? I am getting some questions from you. That's very good. Any questions from anyone of you?
You mean normal water?
Normal water, because normal water contains minerals, right?
Yeah.
Demineralized water may not. But in fact, water has got some minerals. This concept is valid. Please.
Otherwise, the normal water, which is the
Normal water is demineralized water.
demineralized water, plain water.
No, this concept is not valid. Because all the water, all biological substances, it has got some mineral in
And
it.
after filtration, maybe the
Filtration means
RO or
reverse osmosis. I don't know. Through reverse osmosis, mineral can be removed from the
the
water.
mineral, some mineral,
It will be still remaining.
after DM, it may be the
Maybe, but then
Free of
it may also generate magnetic field, may generate oxyelectric field inside it, but it may be the weak. For example, on mineral water, you have to apply very high voltage for the fluid motion, the fluid to make the flow to some kind of channel. But if the demineralized water, reverse osmosis or what you are talking about, it may require high voltage. Still, it has got some mineral. Still, it will generate some electric double layer inside. What is electric double layer? Okay. So here you can see this is the electric magnetic imaging macro form. You can see that we can apply, we can get some pressure difference. Pressure difference from inlet to outlet. So if you apply some applied voltage, so if you are applying some voltage here to electrodes, and you can get the pressure difference. Pressure difference means because it is fluid motion, dispersion pressure difference. If there is a pressure difference, fluid will move. So if we apply some voltage, it's basically creating the pressure difference. This is a primary concept. And also, you can see for different magnetic field strengths, the pressure difference is getting increased. If the pressure difference is getting increased, what will happen? Your fluid motion will definitely accelerate. That is the primary concept. Here you can see the flow rate also getting increased if we apply some magnetic field and electric field together. This is the primary concept. This is the first kind of work that was developed in 2000 by Jiang and Lee in his paper on sensors and actuators. Later on, macro forms for drug delivery applications. You can see here there is a macro form. Macro form is nothing but you are applying some electric field. You can apply some magnetic field together, and definitely you can create. This is a catheter which will be attached with some patient, and this is a flexible drug reservoir. So depending upon the application, depending upon the requirement of drug, in situ application or in situ requirement of drug, then you can basically pump the drug from this drug reservoir to the patient. So this is one of the important applications. So this is the concept that was some German company they have developed this concept in 2012, and these are the you can see in situ manufactured drug delivery device. Here you can see for different kind of electric field strengths or frequency of electric fields, you can generate the flow rate, which is the requirement of the drug delivery. Now, one of the important concepts is why we require this device, because we have injections, we have other kind of facilities. Why this device has got requirement for the medical and non-medical uses? Any answer from anyone of you? Why you require this kind of electric field and magnetic field we are applying, and we can deliver the drug from this drug reservoir to the body of the patient, and we can hack in situ drug reservoir.
Yes. So choose a particular path.
Correct. I want some specific answer. Regulated substance. Yes, absolutely correct. Because regulation is very important. How much drug has to be given to a particular body, that is, through this mechanical pump or through this mechanical sensor which is already available that kind of specific regulation, suppose you want to deliver a drug in terms of microliter per minute, that is very, very difficult to the mechanical devices. So if you have this kind of devices in your hand, you can definitely control your drug delivery through a specific manner.
Targeted supply.
Targeted drug, absolutely, targeted drug delivery is called. Microfluidic devices for COVID-19 testing. Here you can see, this is very interesting. Some group of researchers at Illinois Institute of Technology, USA, they developed this device 2019, 19 afterwards, when the COVID situations come. Here you can see that on a drop of blood, you are injecting in a microfluidic device. Application of magnetic field, one reaction is created. You have some chemical inside this reservoir, microchannel reservoir, and you are just putting a drop of blood to the action of magnetic field. You are making the blood to move to this reservoir. It will have some reaction inside it, and as a result, it will generate some signal. That signal you will connect to the smartphone, and you can diagnose whether you have got a COVID or not. This is one of the devices that has come up. Similarly, barcodes. Nowadays, in all those money transaction or if you go in mall, you have a barcode, right? So in the barcode also, if you put a drop of blood or some samples inside this microchannel, it will flow, and the flow can be made by the application of electric field or application of magnetic field, and it will generate some barcode signal. And through the barcode signal, you can basically diagnose the disease. We call it barcode cell sensor. And then I was explaining paper-based microfluidics, organic-based microfluidics. This paper was published last week actually. And there you can see, you can definitely characterize the dengue virus. You can take a blood sample and put a blood sample in this organic-based microchannels, paper-based microchannels, and it will generate some reactions. And this total this paper-based microfluidic device, you can put on this kind of we can call it controller devices. Controller device, which is basically a combination of electric field and magnetic field together. It will generate some reaction, and through the reaction, it will show some signal whether the patient is affected with the dengue or not.
This is commercially available.
So just introduced 1 week back, this paper has got published.
Right.
This mechanical sensors and actuators by Chakraborty
In India.
Just 1 week back, this paper has got. I thought this may be of interest because dengue is one of the.
This is the top of the hour.
Yes, dengue is one of the biggest pandemic.
Yes.
Now you can see all those stuff. It requires movement of fluid through the microchannels, right? Now you want to understand, or you want to characterize the fluid movement through the microchannel. You need to see what is happening inside the microchannel. Option is you can use theoretical microfluidics. You can apply some theoretical models, or you can have some sophisticated instruments. Sometimes it is very costly. So, in terms of sophisticated instruments, you can characterize the fluid motion through this microchannel, through the application of electric field and magnetic field together. Now, what I have done here actually, we are not basically focusing on the instrumental microfluidics. Rather, we'll develop some sets of governing equations which governs the fluid motion, particularly for the microfluidics, and we can characterize the fluid motion under the action of electric field and magnetic field together. That we will be doing in terms of some case studies. So if you have any questions, please ask me. Any questions? Okay. Let us see, if we apply electric field and magnetic field together, then how the fluid motion will behave inside an microchannel, and what are the different characteristics in terms of flow rate, velocity, and other stuff that we shall explore through the analysis. Before that, we need to understand certain basic aspects of microfluidics, certain basic aspects of how the microchannel works, and what are the physics behind it. Because here, primarily, we are going into the theoretical paradigm. Because we may not have the available facility for the experiments, because the experiments require a lot of investments. We may not have those kind of but with a simple theoretical analysis, you can get the results which is similar to the experimental results. The results you will be getting through the theoretical analysis. Similarly, the same results you may get through your experiments. So why to invest our stuff in the experiment? Let us do some theoretical analysis. Before that, we need to understand what is the basic differences between the macro and micro scale. That I was explaining. You can see Suppose there is a fluid which is flowing through a channel, flowing through a conduit, and the diameter of the conduit, diameter of the pipe, that is 100 millimeter. So simply fluid is flowing, and now what is happening as you move closer to the wall? Definitely, if you move closer to the wall, there will be development of boundary layer. Already you know from the fluid mechanics concept. But we are not talking about the boundary layer. We are talking about, suppose the fluid is aqueous solution, mineral solution, has got some mineral in it, and when it is coming in contact with the wall, it will generate some kind of dissociation of chemical species. If there is a dissociation, what is the phenomena it occurs? That we shall understand through the understanding of elliptical double layer, which is the primary heart of any macrofluidic devices. What is elliptical double layer? How it develops and what are different constituent of it. Just see, when I was explaining that if you have this kind of pipe with diameter is 100 millimeter and there is a liquid inside it or any fluid inside it, if we apply voltage at inlet and outlet, would there be any fluid motion? Yes or no? Suppose this is a pipe with diameter is 100 millimeter. Here there is I am applying a positive voltage here, I am applying a negative voltage here, so that I am creating one potential difference. There is potential difference I am creating. Now my question to you is that would there be any fluid motion?
No.
Fluid motion? No.
Show me, because I was magnetic field is there.
Sorry?
If you are not applying the magnetic field,
Yes.
so far it is not applied, there will be no flow.
Very good. Yes, there will be no fluid. But if you just reduce the diameter by 100 micrometer, then there will be a fluid flow. And that situation we call electroosmosis. Why there is a fluid flow? That we shall understand. We shall see from the concept of electrical double layer. What is electrical double layer? We shall see now. Because any fluid flow to happen, we require some external body force. External body force or external imposing force. For example, this kind of fluid motion, if you want to have the fluid motion through this conduit, you require body force in terms of pressure gradient. You should have pressure gradient. But pressure gradient is manifested when the channel diameter is very small in manifested in terms of electrical body force. It will generate electrical body force. Why it is generating? We shall discuss, we shall see soon. This is the electrical double layer. What is electrical double layer? We shall understand now. Suppose when there is a channel whose diameter is very small, if you move closer to the channel wall, okay, due to the dissociation of chemical species, because a channel has got some ions, and it will get dissociated. Due to the dissociation of chemical species, what will happen? This channel wall will acquire a net charge. Why? Because chemical dissociation is regulated by the pH of the solution. pH, everybody knows what is the pH of the solution. So pH of the solution, regarding with this, there will be chemical dissociation, it will acquire a net charge. Now, ions which are already present inside this flow, it will get attracted by this net charge distribution, and one ion, it will get attached to the surface. Suppose this is the dissociation, it is acquired a negative charge, and ions which are positive charge, it is get attached to the surface. What will happen? Rest of the ions which are not attached with this surface will get distributed bulk in the flow. Okay, is it clear? Yes. Fine. Now we have got two layers. One is monoionic layer, which is get attached with the surface. We call it Stern layer. These ions cannot be moved. If you apply external pressure gradient, these ions cannot be moved. It will not move. But the ions which are already present inside the flow, it will move. Right? This Stern layer and the ions which is present in the bulk of the flow, which can move into get attached to the surface, and the ions which is inside the fluid flow or bulk fluid flow, we call it diffuse layer. And combination of this diffuse layer and Stern layer is called electrical double layer. As a result, there is a monoionic layer which is say positive ions, and some combination of positive or negative ion which is present inside this bulk fluid flow. It will create a potential difference, and the potential difference basically we call electrical potential difference. And the potential difference can be presented or is manifested through a equation is called Poisson's equation for electrical potential distribution, which is electrical double layer. Okay. Another concept is that when there is a charge which is get attached, with the surface, and the potential difference between this layer and this layer, in between this, we call outer Helmholtz plane, and it will generate a charge. That charge is basically charge distribution is called zeta potential of the surface. Well, zeta potential. Zeta potential basically is a manifestation of the electric potential, and it got some implications in generating the zeta potential. It has got some relationship with it. Now, this is the electrical double layer. As a result, development of electrical double layer, it creates some body force. We call electrical body force. So now I was discussing that when the channel diameter is very big, there will be electrical double layer generation. There will be a potential energy difference, potential electrical body force, potential electrical potential generation. But that magnitude is very small compared to the force required to make the fluid flow to the conduit. Now, when the channel diameter is very small, when the diameter is order of 10 micrometer or 100 micrometer, then body force has got some implication. The body force will be very high compared to the fluid present inside the channel, and it may create a fluid motion. It may drag the fluid particle with it, and it will create a bulk fluid flow. So, without applying any pressure gradient, due to this presence of electrical double layer, it will generate electrical body force. It may cause the fluid motion, and that fluid motion we call it electroosmosis. Is that clear? Any questions from this? Please.
Sir, if I change the pole of the bottom layer, then what will happen?
Pole, nothing will same way. It may generate a positive charge, then it will have a negative charge. Then again, bulk, positive, negative charge.
Sir, what's about the bulk layer?
Bulk layer is basically the layer where the effect of this EDM is very good question. I should actually explain it. When bulk layer is there, when this, if you sit here, you will not feel the presence of EDM. Because there is this diffuse layer and the strand layer contains basically it is a elliptical double layer. Now, the effect of surface charge cannot be felt beyond the elliptical double layer. That is called the bulk layer. And the thickness of elliptical double layer, this basically this thickness, diffuse layer plus strand layer, we call Debye length. Okay, we call Debye length. We represent the thickness of elliptical double layer. Please.
Sir, is there any relation of viscosity with this one?
No. But when we will be discussing the steaming potential, what is steaming potential I shall be explaining shortly. Then I'll show that yes, viscosity has got some effect. But in this perspective, since it is completely surface phenomena, surface driven phenomena, there is no effect of viscosity. Any questions?
Can this correct me if I am wrong? It can be said that as the channel thickness decreases, the surface area to volume ratio increases, and that's why this force
will definitely have got some prominence. Correct. Surface to volume ratio is correct. Now we shall do some case studies. Primary objective is to determine or to design smart sensors that I was discussing in the beginning. So, how to characterize the fluid flow when there is a effect of electroosmosis, that is the effect of electric field is there, and also we have got some pressure gradient present inside. So, we shall be doing some theoretical analysis which will give you some estimation of fluid flow, fluid velocity, flow rate, and some other parameters in terms of how the temperature, if there is a temperature present is channel walls are heated, how those stuffs are interacting with each other. When there is a channel height is very small and we are applying magnetic field. Please remember, here we are applying magnetic field, it will generate a magnetic body force, and when it will interact with the elliptical body force, it will generate an additional body force, we call it electromagnetohydrodynamics, EMHD. The concept was first developed by Zhang and Lee paper I was explaining in the beginning. So this is called electromagnetic hydrodynamics, that we are applying magnetic field, there is a pressure gradient, and also generation of electric body force, which is generation of electrical double layer. And if those things are interacting with each other, how the overall situation will behave and how the velocity, pressure, and also the flow rate will behave, that we shall characterize with this analysis. Okay, so for any analysis, what you have to do, you have to have some assumptions, you have to make some assumptions. And these assumptions are very accurate, and if you perform experiments, if you see the analysis results that you are obtaining from this analysis are exactly same from an experimental analysis. The velocity profile will be getting through this analysis. If you perform the experiment with very sophisticated instruments, you will be getting similar kind of analysis, similar kind of results. Here what we have done, that it is a electroosmotic situation. Flow is fully developed, uniform flow, already all of you know. And we are applying one pressure gradient here. Also there is electrical field. Now the magnetic field, what we are giving here spatially varying magnetic field. What is spatially varying magnetic field? That is, magnetic field is varying from, if you consider this is the y-axis, along this along the thickness of the channel, magnetic field is varying. When I was explaining this to some another forum, the participant asked me that how we can get, what is the typical industrial implication of varying magnetic field? Where you can get, in general magnetic field is static, but when you get the varying magnetic field, any idea when we get very magnetic field?
It is an alternating magnetic field, time varying magnetic.
It is time fluctuating magnetic field, but we have some spatially varying magnetic field, some kind of exponential distribution.
In MRI, this kind of principles is the RF wire that spatially varying magnetic field.
MRI has some relationship. The particular answer to this question is, all of you heard of a company called ABB, Asian Brown Boveri? ABB company? Yes. They have developed one instrument where you can get the varying magnetic field, and the variation typically follows exponential distribution. Okay, they have developed recently a smart sensor. They have applied a varying magnetic field, and the variation typically follows exponential distribution. Based on that, it was developed in 2000, around 2002 or 2003. Based on that concept, actually, they have developed one instrument, and then through the instrument you can get this kind of variation. And later on, they implement their idea in the steel industries. In the steel industry, we call flow control mold. All of you know the continuous casting process, because why I am just explaining this, because it has got some relationship with that. All of you know the continuous casting process, right? Continuous casting, liquid steel is poured in a mold and it gets solidified. It is going well. Now, in the continuous casting process, if you want to increase your casting speed, what will happen? There will be a huge fluctuation of the liquid steel inside the mold, right? Now, if there is a huge fluctuation of liquid steel inside the mold, what will happen? There will be entrapment of the slag layer which is present over the liquid steel layer, and the slag layer entrapment will cause some defects inside the steel, right? Well, the steel makers could not able to achieve casting speed beyond certain value. Later on, ABB has introduced their idea, and they designed a special type of mold called FC mold, flow control mold. And then flow control mold, they apply this kind of typical exponential variation of magnetic field. The beauty of this is that if we apply some magnetic field, it will suppress the fluid flow. Fluid flow is getting suppressed, and if the fluid flow is getting suppressed, the turbulence created by the fluid flow also gets suppressed. The turbulence gets suppressed. This fluctuation also, we call it mold level fluctuation. Fluctuation at the mold will also get suppressed. Then the possibilities or probabilities of slag layers to interact with the liquid layer also get reduced, and they have got very good quality speed, and they could achieve a casting speed. Initially in 90s or 1995, 1996, if you visit steel industry, they used to run a caster around 1.1, 0.9, 1 meter per minute casting speed. Nowadays they are running 1.7 meter per minute. Huge enhancement in steel production.
Is it only applicable for FE casting?
For flow control casting?
No, flow control casting only for iron, because since it's a magnetic.
It can also apply for aluminum, nickel industries, copper industries also possible.
It is possible.
Yes, but they have generally introduced aluminum is Norco, they have got this kind of mold, and also Tata Steel and Jindal Steel, they have also this kind of mold.
Magnetic field generally has an affinity towards iron.
Correct, but it will create some situation where this fluid is given the fluid temperature. Temperature is around 1500 centigrade, liquid steel temperature. The affinity of magnetic field of the with the steel, it will not basically it will be ferromagnetic beyond 1000 or so. Temperature is 1500, so there is no such issue. They claim that. It is basically happening. If you visit some steel industry, most of the speculators they implemented this idea. And it is this idea of great success. Later on, this idea was tried to implement it in a mapper channel. Mapper channel they created some special variation in the magnetic field. They found that there is a really enhancement in the flow rates, and sometimes they are getting better, particular directed flow velocity, but you can enhance the flow rates through mapper channel. And that analysis, and that gave us the idea whether we can do the similar kind of analysis for the mapper channel flow or not. And there is a combination of electric field and magnetic field together. Lot of equation and lot of stuff. I'm not going into details, but just I'm giving you an idea. Here you can see ions, liquids, this fluid which is fluid where henceforth sometimes. Ions, if you consider the molar volume function of the ion, then molar volume function, or if you consider size of the ions, it may create some additional implications in the fluid flow. We call it steric effect. Steric effect is that if the volume fraction of the ion, basically at a particular small region, if you consider the volume of the ion, then we call this situation has got some steric effect. But if you do not consider volume of the ion, if we consider point charges, then we neglect the steric effect. But here, in this analysis, in general, if you just extend your analysis for any industrial application for development of smart cities, you require the consideration of steric effect. And this gamma basically is a representation of steric effect. We call it molar volume fraction of the ion. You can see, if you do experiments, if you want to calculate or if you want to perform some analysis with considering the molar volume fraction of ion, you can understand what kind of sophistication is required, right? It is very, very difficult. I do not know whether in your Indian perspective we have that kind of sophistication or not. But through some theoretical analysis, fundamental principles, you can consider the molar volume fraction of ion, just introducing this parameter. How these things are coming, that requires certain assumptions, certain derivation from the electrochemistry part. That I am not going into details. But just remember this. This is basically ionic number density, how much ions are present. What is the probability of the ions in a particular channel when the fluid is flowing? It can be represented by this expression, and where in this expression gamma is the molar volume fraction of the ion. You can derive it from this equation. You can derive it. The derivation I am not going to do. Again, yes.
So, one thing, this psi you are putting, that is the potential, that
yes,
is equal to zeta potential y equal to plus minus 1.
Correct.
Zeta potential, as we have mentioned, it is the potential at the end of the boundary layer.
Not boundary layer, star layer. Star layer, yes.
Okay, so this I can see that y equal to 0 is the wall.
Yes.
Then plus 1 is star at the end of star layer, but minus 1 is
monoatomic thickness of the ion. Okay. So in general, in a theoretical analysis, we can just neglect thickness of that ion. It is now some angstrom level.
Yeah.
So you can neglect it.
So then y plus minus 1 is going to signifies what?
Y plus minus 1 signifies the wall. We are basically, see, Stern layer, basically the physical definition is that the zeta potential basically defines the potential between the Stern layer and the bulk fluid layer. We call it a diffuse layer, sometimes we call another. Now, that layer, since the ionic, while doing the analysis basically, we generally consider the zeta potential value at the wall because the thickness of the ion is in terms of angstrom. That angstrom level difference basically can be neglected through this introduction of the
y equal to 0 is at the end of star layer and not at the wall.
Y equal to 0 is really central level because I just see, you just see this. No. You just see this. Previous slide. Yeah. This is the y axis. Y equal to 0 is center line?
Center line.
Yes, symmetric condition. Center line, this flow speed is very small, low elastomer flow, creeping type of flow. And y equal to plus 1 is here, upper wall, y equal to minus 1 is here, the bottom.
Okay, we are not considering wall, we are considering at the end of the star layer.
Oh, you understand? Okay, now anything, so the ideal potential distribution, if you want to find estimate what is the potential that is created due to the generation of the ideal, it can be defined or it governs to this Poisson-Boltzmann type of distribution. The standard potential distribution which is present in kind of ideal configuration. Now anything actually this kind of distribution distribution. And here rho is the net charge density. This is basically this is stuff from electrochemistry. Rho is the net charge density, and it can be explained in this way. Here is basically valency of the electrons. Now for a symmetric electrolyte, we can write this ideal potential distribution in terms of dimensionless form d2 psi by dy2 equal to lambda by 2 sin hyperbolic 4 psi by 1 plus 4 theta sin 4 theta. What is this? Psi is the dimensionless ideal potential distribution. Electric doubly it has got some potential distribution. So dimensional ideal potential distribution is the psi. Lambda is basically inverse divided length. Kappa is the divided length. Divided is the thickness of the ideal. So inverse divided length is lambda. And psi is your dimensionless ideal potential, and y is the dimensionless. Why are we dimensionless? Basically, in general for the analysis, we make all the bounding equations dimensionless. Any questions from in this slide? From anyone? Any questions? Please. A lot of mathematical equations.
Sir, what is A in lambda?
Lambda equal to
A by K.
A by K. Kappa actually. Kappa is basically your dividend.
What is A?
A. See, half channel thickness.
Yeah.
Yes. Clear? Understood? Also, here also you can see this is a channel where we have applied specially very magnetic field. Here, the channel ones are maintained at a particular temperature, world temperature, TW. We call it world temperature.
Sir, one question. If it is a symmetrical, means you are applying the varying magnetic field. Exponentially it is varying. But if we use in the parabolic way, just in the middle portion it is maximum and gradually
You can also try. That will be a second thought of this research work. You can extend this research with this kind of parabolic magnetic. That's a very good research.
Is it possible to do?
It's possible. Try it.
Okay, thank you.
No, you can get a lot of analysis results. Write a paper also.
Yeah.
Okay, this is the ideal potential. Ideal potential. But another important is you have to justify where you are getting this kind of parabolic magnetic field. Okay, the justification is required. Now, this part already you know because due to the action of electric field, it is creating some body force now. We call it Lorentz force. I was explaining a few slides back. And this magnetic field has got some dependence, so has some functional dependence. Now, functional dependence, whatever we have been implemented here, the same functional dependence was implemented by the ABB while developing the instrument. Dependence is basically B0 static magnetic field into a function of R, y by A into direction is y direction. EY is the unit vector of the y direction. Okay. With this, if we just substitute this equation in the Navier-Stokes equation here, and finally if you make the equation dimensionless, you will be getting this kind of equation. Okay. Now you have got the equation in your hand. With this equation, you can analyze the entire situation. If we just tweaking the magnetic field, if you can tweak the data potential or wall potential, you can characterize what is the fluid flow and other stuffs. Here one of the important parameter is here is the HA. HA basically is what we call it Hartmann number. All of you know, Hartmann number is a manifestation of strength of magnetic field. If the magnetic field is very high, Hartmann number is very high, similarly vice versa. And this gamma, capital gamma, basically is the strength of pressure gradient. Because here, in this situation, we are applying the magnetic field and pressure gradient together. Right? So, due to the pressure gradient, we have some stuff. Due to this pressure gradient stuff, because if it is positive, there will be positive flow direction. If it is negative, there will be back flow. So, you can manifest it with this pressure gradient. Again, this is the final equation with the boundary condition y u at upper wall is 0 and u at lower wall is 0. No slip boundary condition. Because fluid motion has to be arrested at the wall, and we call it a no slip boundary condition. And this is basically. Now here one important consideration is the Ry part. We need to know what is the value of Ry and how the magnetic field is getting distributed through the entire channel. So based on the methodology developed by ABB during their experimental setup, here we have also assumed Ry as an exponential distribution, exponential minus beta y. Beta is actually constant parameter. So you can tweak the beta, you can change the magnetic field distribution. Accordingly, you can get the fluid flow motion for different situations. Again, what I was explaining here, because the channel walls has got some temperature, If there is a temperature, what will happen? There will be thermofluid motion. Temperature will interact with the fluid flow, and as a result, you have the velocity equation in hand, but you equal also energy equation. For this kind of flow, all of you know that we have got two kind of flow situation. One is called thermally developing flow, or one is thermally developed flow. The flow is already developed. It's called thermally developed flow. The flow is not developed. It's developing around the length of the channel. It's called thermally developing flow. So here we have considered the situation, second situation, which is very much practical for smart sensor development. It's called thermally developing flow. So you have considered thermally developing flow. The flow is slowly developing around the length of the channel, and as a result, if you analyze the thermally developing flow consideration, you have to consider energy equation. So energy equation is something like that. The rho Cp u dt dx equal to k is thermal conductivity, u the fluid velocity, d is the temperature. And this part is the body force term. One is body force term is due to the viscous distribution. Because if the fluid is flowing to the macro channel, there will be a continuous fluid friction with the wall. As a result, it will generate some heat. That heat is manifested to the viscous distribution. This is the viscous distribution term. Another is term SF, we call it joule heating. Joule heating because there is ideal potential creation, because electric field is created SF. And as a result, it will generate some effect due to the heating effect, we call joule heating. Sigma E is the standard expression of joule heating. So we have two body force due to viscous distribution, body force due to joule heating. Okay. Again, the primary objective is to get a solution of this problem. Now, you just make this equation dimensionless with this dimensionless parameter. You will be getting that x2 minus br del u del y whole square minus sp. Br is basically how much viscous distribution is creating this equation. The manifestation of viscous distribution. Sp is a constant term, is a manifestation of joule heating. If Sp is very high, your joule heating is very high. Sp is low, your joule heating will get reduced. Okay. Accordingly, another important parameter would be your bulk mean temperature. Bulk mean temperature definition already you know. That is standard mathematical stuff, textbook stuff. Bulk mean temperature. So this is the bulk mean temperature. Okay. So. Okay. So this is the bulk mean temperature theta m. You know the definition of bulk mean temperature. Basically, it is a manifestation of average temperature to this macro channel. And accordingly, you also calculate a Nusselt number, or sometimes we will call Nusselt number, but pronunciation is Nusselt number. German scientist, we should call it Nusselt number. So Nusselt number is 1 by theta m d theta del y at the wall. So already you know this stuff, how you can calculate the Nusselt number, temperature distribution for thermally developing flow kind of considerations. Here, if you want to solve this equation, you got the boundary conditions. At inlet, you have a theta equal to T minus Tw, Ti minus Tw, this is a dimensionless temperature. So at inlet, your Ti equal to Ti inlet temperature. So theta would be definitely 1. At the channel walls, T equal to Tw. So it will be, Tw will get cancelled, it will be 0, theta plus minus y. As a symmetric flame, or we have what z del y 0, and other stuff basically is a long channel. Theta will be some less than some parameter, it will channel length is very long. This is the 4 boundary conditions that is given for these typical boundary equations. So what is your task? Your task is to get a solution of this partial differential equation, energy equation, along with your velocity equation, and also this ideal equation. So you have got 3 equations, right? Because this is theoretical analysis, so you need to solve some governing equation with the boundary conditions. So you have developed a boundary equation and with the boundary condition from the first principle. So we have got ideal equation. This is the ideal equation. Second one is your velocity equation, and third one is your
black body white body না হবে ব্ল্যাক বডির উপরে হবে কিন্তু এটা সাদা হলে তো স্ক্রিন তো আসছে না স্লাইড চেঞ্জ হবে ও স্লাইড চেঞ্জ হবে ঠিক আছে আমি দেখুন
So this is the second equation is velocity equation. Third equation is in your energy equation with the boundary condition available in here. So you have to solve these three equations. The good thing is that I solved this equation, these three equations, through a computational fluid dynamics technique, CFD. Okay. So here in MATLAB, simple MATLAB software, everybody has got some MATLAB software, right? Through MATLAB, ordinary differential equation solvers are available, or some solvers are available. Simply ODE solve. Just please read ODE solve and you can obtain the solution of this temperature, solution of this velocity, and solution of this ideal potential distribution. Because you require initial ideal potential distribution equation to solve first, followed by once psi is obtained, then you have to put the value of psi in this velocity equation, you have to obtain the velocity equation. Let's do the velocity first. Okay, once this solution is obtained, then this equation, you have to put this temperature equation, then you have to have the solution for temperature. That means all these three equations are coupled. Firstly, you have to solve the ideal. Second, once the ideal solution is obtained, followed by next step is to solve your velocity equation. Third is you have to solve your energy equation. All these three equations have to be solved coupled manner to obtain the velocity and temperature distribution instead of aperture time. Any questions?
Sir, is it possible in analytic method?
Possible. Possible. But here you can see the characteristics of the equation. Because we have considered the steric effect, the gamma part is present here. If gamma is 0, that is when we consider point charge. Charge is point charge. Then what will happen? d2 psi by dy2 equal to some constant equation and how to equal psi. This equation analytically tractable. I will show you one solution when we have considered gamma is 0. But this velocity solution, here also you can see this is complicated non-linear ordinary differential equation. You may not have the solution and the solution available, but ODE function, MATLAB ODE function, and another very important solver you may like to note it, CHEFFUN, CHEBFUN, Chebyshev polynomial based solution. It's very strong mathematical function available with the MATLAB. They have introduced recently CHEFFUN, CHEBFUN, CHEFFUN. Just use the CHEFFUN solver. You will get the solution. This kind of non-linear partial differential equations. MATLAB, yes. CHEFFUN solvers are available nowadays. It was not there long back. Nowadays it is available with the MATLAB. So you have a solution available. Now you can get the velocity distribution. You can get a temperature distribution. Let us see the velocity profile first. In the first graph, you can see the velocity profile. At h equal to 0, there is no magnetic field. You have got typically parabolic velocity distribution. Simple flow distribution when there is no magnetic field. But when the magnetic field presence is there, for example, at h equal to 1, beta equal to 0, beta means exponential part is not present inside the magnetic field. What will happen? The flow velocity is getting suppressed. You can see flow velocity is getting suppressed. Why? Because magnetic field creates some body force term, Lorentz force term. Lorentz force term is impeding the fluid motion, it is restricting the fluid motion, right? If you restrict the fluid motion, the velocity will get suppressed, and you will get some kind of plaque type velocity. We call it plaque type velocity profile. Again, if we introduce the beta term, that is, we call it spatial variation in the magnetic field, what will happen? You will get some velocity distribution which is not symmetric. You will get asymmetric velocity distribution when there is a beta term presence. Beta equal to -1, beta equal to +1. So you can see how beautifully you can maneuver the fluid motion in the macro channel if you add the ABB instrument which has got exponential distribution to the fluid motion in that. So suppose you have a Lavoisier, and Lavoisier you want to have preferential fluid distribution, of the sample in a particular direction. So if you apply this kind of spatially varying magnetic field which has got some preferential distribution, you can have distribution of fluid flow along the positive y and distribution of fluid flow along the negative y just by tweaking the parameter theta. Correct? So you can see what is the direct implication of this analysis for the design of and development of smart sensor, not only for the biomedical application but for different industrial applications also. Okay? Another part is if you change, so I was discussing that in general we consider charges are to be point. So point charges consideration. when the effect of volume fraction of the charges are neglected. But here we have considered the volume fraction of the charges. So here you can see, if we change the volume fraction of the charges, how the fluid motion will change. So for the first case, when charges of point are neglected, that is zero, gamma equal to 0, gamma equal to 0, and if we increase zeta potential, zeta equal to 1, zeta equal to 3. So from line zeta equal to 1, so this is zeta equal to 1. Okay, this is zeta equal to 1, and zeta equal to 3. So when we are considering the steric effect, charges, we consider the steric effect, what will happen? That increasing the zeta potential, surface charging effect, it will create the fluid, bulk fluid motion very high. So there will be a generation of ionic species in the bulk fluid motion, concentration of ionic species in the fluid will increase. It will direct the fluid motion, electrostatic fluid motion very fast, so you can get the enhancement in the flow rate. You can see, compared to the situation, your charge, your fluid motion is getting enhanced when you are considering a higher value of zeta potential. But interestingly, you can see, actually it was found in my research only, that if we consider the effect of charging, effect of steric parameter, volume fraction of the ion, say gamma equal to 0.3, gamma equal to 0.3, gamma equal to 0.3, this chain dot line and long dash line. So gamma equal to 0.3 is chain dot line, gamma equal to 0.3 long dash line. If we increase the zeta potential, your velocity is getting decreased. This is other suppressed. This is other way around. Why it is happening? Why it is happening? So in one case, when we are considering the effect of volume fraction of the charge, velocity is getting increased, velocity value is enhanced, if your surface charging is increased. But in the other case, when we are considering the volume fraction of the ion, the velocity is getting suppressed. Why it is happening? The answer to this question is that basically we tried a lot actually. Initially we could not able to get the answer. But later on I found out that, see, when there is a consideration of surface charging and also there is consideration of steric effect, if we increase the molar volume function of the ion, it will generate a closed plaque layer at the wall. So maybe I will draw it in the board. Should I draw it? Actually, what is happening? This is the wall. Is it visible from the sides? Well, I will record this board while explaining the steering potential. If I explain it, it may sound abstract, but I will explain it in some analysis. So, this is the wall. When I am considering the zeta potential, if you consider steric factor here, say it is gamma 0.3. If we consider the zeta potential, so first case, this is the layer, stern layer, right? Yes. Stern layer, this let us say this is negative, this is positive ion. Just if you see the ideal potential distribution, this is the y-axis, ideal potential distribution looks like this. At the wall it is very high, at the center line it gets reduced and gets to be 0. So this is the ideal potential distribution, psi of y, this is your y-axis. Now you can see, when we consider the effect of steric parameter at a situation, then what will happen? For increasing the zeta potential, it will form a closed plaque layer, that is formation of stern layer. Now the question is, formation of stern layer is anywhere there. But if we increase the zeta potential, the volume fraction of the ion will get increased and it will generate this kind of volume fraction of the ion. That is size of the steric length, or you can see if we just consider this thickness, let us say lambda will get increased. For example, when zeta equal to 1, you will be getting this kind of value, and when zeta equal to 3, the formation of stern layer, it creates gradual drop in the ideal potential. If there is a gradual drop in ideal potential, the body force which is required to move the flow along the particular direction, it it will definitely get reduced and fluid velocity get reduced. This is the physics behind this. If you consider the effect of Stern layer, if you consider the effect of steric parameter, why your fluid velocity get reduced if we increase the zeta potential. Is that clear? Any questions? This is the one of the important understanding, because sometimes during experiments or while designing the any kind of smart sensor devices, we generally do not consider the effect of this steric parameter. But this effect of steric parameter has to be considered because it has got huge implications in terms of fluid motion or fluid transport characteristics. Any questions?
This is why that dotted line gamma equal to 0,
Yes.
beta 3, it is coming down and then moving up.
Then moving. Okay. Then temperature distribution, straightforward. So because we are thermally developing flow. So all of you know thermally developing flow. It is understood by everybody, I hope. So you can see that at different axial locations, that means if you see, this is your macro channel. So suppose this is your x direction at x equal to 0.5, x equal to 5, and this is x equal to 10. At different locations, I have plotted the temperature profile. So x equal to 0.5, you can see you get this kind of temperature profile, and definitely there is a suppression of temperature, because if there is suppression of temperature, it will be actually a magnetic field. Why? Because if you have a magnetic field, it will suppress the fluid velocity. If there is suppression of fluid velocity, convection heat transfer from the wall to the fluid flow definitely will get reduced, and heat transfer will get reduced. Similarly, for all the locations, you can see temperature profile is changing because it's a thermally developing flow. Temperature is not yet developed. Actually, if you just see this at an inlet, you have some fluid is entering at a particular temperature, the Ti. Immediately when you enter the channel, it will not develop the temperature profile like this. It will gradually develop. And at a particular location x equal to 10, it will fully develop the temperature profile. So that is called thermally developing flow and thermally developing considerations. Here you can see for all the cases, again, application of magnetic field causes suppression of temperature magnitude. That means it has got a huge implication for the design of smart sensor. So when I was explaining that this high performance computing system where we require this microchannel based cooling system, if we apply this specially very magnetic field, you can definitely reduce the temperature, or you can definitely reduce the heating effect caused by the high performance computations. Right? So that's why you can see here also, for different magnetic field strength, if you tweak the magnetic field variation by changing the parameter beta, you can definitely suppress the temperature. It is one of the important analysis or important result from this analysis. So finally, the primary task is to Nusselt number distribution, Nusselt number distribution, how the Nusselt number is getting distributed. So what is the typical, just let me inform you that this is a typical Nusselt number distribution for macrochannel flows. And what is the special unit? Can anybody answer this? So what is this? This is the inlet. This is the inlet, and we are moving along the axis of the channel. Okay, this is the inlet. We are moving along the axis of the channel. What is the special Nusselt number? Basically, Nusselt number is the manifestation of heat transfer. Nusselt number is very high. Heat transfer will be very high. If it is less, heat transfer will be definitely less. What is the special unit? You can see from the inlet. This is the inlet. When the fluid is entering in the macro channel at a particular temperature Ti, there is a drop in the Nusselt number, drop in the heat transfer. But at a particular axial location, there is sudden discontinuity. Okay, so after the discontinuity region, temperature is getting reduced, heat transfer is getting reduced, and after that, it will become axially invariant. Okay, and this axially invariant location we call thermally developed location, but there is no change in the Nusselt number. So So what is happening here at the intake? Temperature is very high. Development thermal boundary layer causes the high heat transfer from the water to the fluid. Fluid temperature will get increased. If the fluid temperature is getting increased, what will happen? Your bulk fluid temperature will also get increased. That means, if we see the definition of Nusselt number, it is basically your some gradient by bulk fluid temperature. We call it theta. Theta is the bulk fluid temperature. So at the inlet, what is happening here? There is a development of thermal boundary layer. Thermal boundary layer causes high temperature gradients. As a result, your bulk fluid temperature will also increase. If the bulk fluid temperature increases, what will happen? Your
Nusselt number decreases.
is decreasing. But at a particular axial location, there is a bifurcation. How to needs continuity? Why? Because in that location, bulk fluid temperature becomes closer to the wall temperature. And in that case, bulk fluid temperature here near some location, this bulk fluid temperature theta m is tending to wall temperature of the mapper channel. That means it tending to a value of 0. Very small value. If there is a very small value, then what will happen? The denominator term will tending to 0. So third bifurcation. Okay. After the bifurcation region, it will again decrease because bulk temperature will again increase. Why? Due to the heat generation due to unity and viscous distribution. Because you can see in the energy equation, we have considered unity and viscous distribution part. And due to the action of unity and viscous distribution, again the fluid temperature will get increased and bulk temperature will also increase. And as a result, fluid temperature inside the member channel, it will exceed the wall temperature. Because wall temperature is the primary constant. Here, the wall temperature will never exceed the inlet temperature. But at this, beyond the location of bifurcation, wall temperature, fluid temperature will exceed the wall temperature due to the action of unity and viscous distribution. As a result, theta m again it will start increasing. As a result, if theta m start increasing, what will happen? There is a gradual decrease in the Nusselt number. After certain time, say x equal to 10 or so, this theta Nusselt number become axially invariant. As a result, we have an axially invariant temperature profile, and this condition we call thermally developed flow. Thermally developed flow, now thermally developed Nusselt number.
That's become steady.
That means a steady temperature, steady heat transfer will be getting. So this is thermally developing region. Thermally developed region temperature has not yet developed. After that, it is already developed. So you have got a constant Nusselt number value for the length of the channel. Okay? Any questions on this? Any questions from any one of you? Please ask me if you have any doubt. I am happy to answer. Or you can ask in terms of application-oriented question. Because anyway, final objective is to apply this concept for the design of smart sensors. So that means here you can see also that again, if you increase the magnetic state, your heat transfer will get reduced because Nusselt number value is getting reduced. So this is a very important figure. This is the decision figure. Whatever analysis we have done, from this analysis, we can decide from this figure what range of beta and Hartmann number we should consider to get a maximum heat transfer. NFT is the Nusselt number value when Nusselt number is axially invariant. This is the region, this is the value of Nusselt number NFT. For example, around 2 or so. You can see, you can tweak the beta and Hartmann number. This is a three-dimensional plot. Here we have shown the variation of fully different Nusselt number with beta and Hartmann number. So we can tweak beta and Hartmann number together to obtain a maximum heat transfer in this region. You can see around beta equal to 5, Hartmann number is around maybe this region. You can get a fully developed Nusselt number for heat transfer. So that, for example, for industrial implications, that is for the design of smart sensor, smart actuator for high performance cooling, we require to maintain your beta and Hartmann number value in this range to obtain a high heat transfer. Fine? Any questions?
Sir, FD means they are fully developed.
Correct, because what happens, this is the value of Nusselt number. So this is called fully developed Nusselt number. Beyond which there will be no change in Nusselt number. Because here Nusselt number is changing and subchanging. After that, when it is reached the thermally fully developed region, there is no change in Nusselt number. So you have got fully developed Nusselt number value, which is basically NFT here. This is one of the design consideration, design parameter from which you can understand what is the value of Hartmann number beta we should consider to obtain a corresponding value of heat transfer height.
Sir, once it is fixed, but the rate of heat transfer would be the minimum. But here,
No,
the
no,
rate to
no,
the rate.
it's not like that. It's not like that. See, it is not a minimum. It's not a question of minimum or maximum. It is question of, suppose you have designed an upper channel and you have some parameter in your hand. You are making some aqueous fluid and aqueous fluid flow into the upper channel. So, what is the heat transfer that you are getting for the fluid motion to the upper channel? The answer is NUF. So this is a region we should not consider because it's an unstable region. Flow is not yet stabilized. Thermal profile is not yet stabilized. But thermal will be stabilized after this region. So the heat transfer perspective we should consider for only this region because here you get stabilization in heat transfer.
Okay, I understand.
So that is a design economy. That's why. Okay. Any design requires N2 generation analysis, right? If you have a high heat transfer, if you have a high fluid flow, but you require N2 generation to be minimized. What is N2 generation? Disorder of a system. So our disorder of a system has to be minimized. So here you can see we can have disorder in terms of two consideration: disorder due to viscous dissolution or fluid friction, disorder due to heat transfer. Summation of these two parameters basically determine total entropy system, total entropy generation of the system. So you can calculate the entropy generation and you can see what is the total entropy variation along the Nagel channel and how it is behaving and for which value of parameter your entropy generation is minimum. Right? This analysis is very, this analysis are phenomenal analysis. Many people have tried for different systems. But I generally, my consideration is that we should not do this analysis unless we don't know what is the objective of your work. If your objective is fixed, then you can do this analysis to obtain the typical value of parameters for which your disorder in the system is minimum. So disorder means basically if your entropy is minimum, your heat transfer should be optimized. So while with the optimization analysis, you should do this kind of analysis. Otherwise, there is no point of requirement this analysis. Here you can see the total entropy generation parameter. If you see the variation, it is follow this kind of profile. At the wall, entropy is maximum, but at the center line of the channel, entropy is minimum. Why? Because at the wall, your temperature gradient, fluid velocity gradients are very high. Due to the presence of thermal boundary layer and velocity gradient. High temperature gradient, high velocity gradient. The gradients are very high, definitely you have high entropy generation. But at the center line of channel, gradients are getting decreased. So here you have a minimum entropy generation. Accordingly, one can also calculate a number. It was given by a famous scientist called Adrian Bejan, Duke University. So, based on his name, is a number called Bejan number. So, he is still very much active in this heat transfer, fluid flow areas. Bejan, Adrian Bejan, he got some lot of books in heat transfer, fluid flow, also thermal fluids. He is one of the expert in that area. So, Bejan number basically is the dominance of heat transfer in irreversibility is theta entropy due to heat transfer by total entropy. Heat transfer due to fluid friction plus entropy due to heat transfer. You can see when the Bejan number, how the Bejan number is varying along the x length. So you can see this is a typical variation of the Bejan number. In general, please note that when the Bejan number is greater than 0.5, we call it the system is dominated by the heat transfer irreversibilities. When the Bejan number is less than 0.5, we call it system is dominated by the fluid friction irreversibilities. This is a thumb rule given by scientists and researchers. That when the Bejan number is greater than 0.5, we have a system which is dominated by the heat transfer irreversibilities. When the Bejan number is less than 0.5, we have a system which is dominated by the fluid friction irreversibilities. Here you can see by increasing the duality parameter for certain systems, we have a Bejan number which is less than 0.5. For example, SP equal to 1 when duality parameter is closer to 1, with the entire system is dominated by the heat transfer fluid friction irreversibilities. That means when the duality parameter is very high, it will cause more homogenized mixture in the fluid flow, and as a result, this fluid friction irreversibility will get increased. You will get total system will be dominated by the fluid friction irreversibilities. But for other cases, for low value of this parameter, duality parameter, you have a dominance of heat transfer irreversibilities. Okay? Why this is required? This is required for design of smart sensor definitely and entropy minimization optimization. So you have to minimize your entropy so that you can get optimization in heat transfer optimization. Any question on this? Okay, so let us proceed further. Another case test we can immediately do. So findings I am not going to detail because already I have explained in this class. Okay. This is a case study that when there is a harmonic developing flow and okay, so I have to go fast actually. Now, this is a situation for harmonic developing flow, EMG transport with the interfacial slip. Here I am going to answer your question. So can you solve the equation analytically? Yes, I will show you it is possible to solve this equation analytically. It may be interesting for all of you. So again, this is a situation, simple situation. Just see how by just carrying out simple analysis we can answer answer to the questions for micro channel flows which cannot be performed without having a sophisticated instruments. Just by simple theoretical analysis you can obtain the results which is at par with the experimental results available in the literature or some other sources. Here you can see there is a fluid flow in a micro channel. There is no electrical field applied. In the first case, we are applying some electrical field, but in the second case, we are not applying any electrical field. There is a only fluid flow. There is a magnetic field applied. Is applied magnetic field, and as a result, what is the typical consequence we shall see when there is a only pressure gradient which is applied in the magnetic field. That means this is the situation when there is no electric field, only pressure field, pressure gradient. So we have some micro pump which is attached here and it is throwing fluid to the micro channel as a particular pressure gradient dPdx. Okay. In addition to that, we have only static magnetic field which is applied in the vertical direction, the y direction, in this direction. As a result, it will generate a Lorentz force which will be acting along this impact the fluid. Now, here we introduce the concept of slip and steering potential. Let me discuss one thing. Steering, what do you mean by steering potential? And what do you mean by slip? Already all of you know what is slip. Slip is known to all of you. Okay. Let me discuss what do you mean by steering potential. This is very important for you can see the second consideration or second physics from the perspective of micro channel flow, which is called steering potential. Steering potential. Steering potential. Okay. Suppose this is your micro channel. Micro channel. Please see this. This is a very simple understanding. Fluid is flowing as a result of applied pressure gradient minus dPdx. Okay. Now, what will happen? There are ions present in it. So at the wall we have a strand layer, and inside this we have a diffuse layer, right? Bulk layer, so you have a both positive and negative ions. This kind of ions are present. As a result of applied pressure field or applied pressure gradient, what will happen? Fluid will start moving in this direction. Correct? Isn't it?
Yes.
So what will happen? These ions will also move with the fluid motion, and it will start to accumulate at the end of the channel. Let us say this is the inlet, this is the outlet. So near to the outlet, there will be a preferential accumulation of the ion. Here we call it
due to migration, due to the action of pressure field, there will be differential accumulation of the ion at the end of the channel. It's quite straightforward, right? Now ions are moving in a particular direction. If there is an ion movement, what will happen? It will generate a current. Fine? It will generate a current. We call it steaming current. IS. Now how the steaming current is evaluated, I will show you. We call it steaming current. Now,
So the ions in the bulk of the fluid, that is some kind of mixed charge, right?
yes.
So if they move in one direction, so then there can be two or one.
I'll come to that. When knowing this, right? You know this? Okay. Good question. So there will be steaming differential accumulation. So there will be steaming ions are moving in this direction, and then there will be current generation, right? So steaming current, IS. We call it steaming current. Steaming current. Now, as a result of differential accumulation of the ion at the end of the channel, as Professor was explaining, telling me, there will be another current which will be acting on the opposite direction. Is that it? Are you agree with me?
Sir, how? Opposite current.
There is accumulation of the ion. Both positive and negative ion, accumulation of the ion. Now, as a result of accumulation of ion, there will be potential difference.
Yes.
So, as a result of potential difference, there will be opposite direction current flow also. Right? We call it IC for conduction current. Or conduction current. Okay? And steaming current in this direction, conduction current in this direction. As a result of movement of these two currents, there is a potential generation of electric potential generation of the. So if we attach some wire here, some cable we are attaching here, and we also attach some cable here. If we measure the potential difference, you will get some volt. Right? You get some volt. This potential we call steaming potential or E. Is that clear? That means just by a fluid motion inside the Lapa channel, we can get a voltage difference. With a voltage difference, we can lead a light, small light. We can attach the light here. So we can lead. That was possible. It was shown by some group of researchers recently from IT report. They have shown that it is possible. Just this potential voltage difference, due to this steaming potential, we can get some potential difference, and with this we can generate some electricity. Right? Also note that these star layers also is there present. Right? Star layers also create a current, which will act along this direction. I don't know which direction. It will depend on the presence of star layer. So this star layer we have also current. We call conduction current due to star layer. But in general, you can see the flow is neutral. Right? It will not show any differential positive ions or positivity or negativity or positive pH or negative pH. So as a result, under stable condition, this steaming current, summation of all current, that is steaming current, conduction current, opposite direction, plus conduction current in the star layer is 0. And this condition is called electroneutrality principle. I will come to that. It's called electroneutrality principle. We call electroneutrality, and through which you can calculate how much steaming potential is developed inside the matter channel, and how much electric voltage you can get, and through which a small, maybe very tiny microlamp we can lead. Fine? Any questions from anyone of you? I was getting some interesting questions, a few of you. Any questions? So, just theoretical analysis. Yes, please.
Sir, if it is a steady flow device, so how then the ions are accumulating? It is drainage out.
It will not. Another interesting question. So, what we do actually, we add one reservoir here. Also, we have one reservoir here. So, basically, here we have inflow, one reservoir. We add a microphone, which is again to the inflow. Clear?
Yes.
Any questions? And the flow velocity is very small. Or Reynolds number is order of 10⁻²-3 sometimes.
That's why it is happening. It's called creeping flow paradigm or creeping flow regime. Okay. So now we do this theoretical analysis and we'll show you is it possible to have on just sitting in a table and chair or just sitting in a chair and having only one small computer, desktop computer, you can do the analysis and you can do great analysis which can have merit in publication. Yes.
Sir, in the absence of any electric current, so how the Lorentz force will be generated? Because it is the just cross product of B and J.
Correct. Streaming potential.
Streaming potential.
Yes. So in the absence of any electric field, if you only have resonance channel, we can get the streaming potential and also we can get the corresponding magnetic field. Okay. So now I will show you some things. Just extension of this analysis. We have only streaming potential. So again, I am not going into details. Just see this. We do not consider point charge. So gamma part is 0. This is our equation. If we make the equation dimensionless, it will be d2 psi by dy2. Already I have shown. This is just analytical solution. Simple analytical solution. Use Mathematica. That's it. Okay. Or simple Mathematica. You can do this analysis solution. Or some mathematical tools. Online. If you don't have mathematical software available with you, online differentiation, online integration. Lots of sites are available online. Just use this. You can get this solution. Okay. Another is Debye-Heckel linearization, that is when theta potential is very small. This equation can be written as d2 psi by dy equal to Ez psi kb into t, because for small value of theta potential we call Debye-Heckel linearization. But here we can get when that is we call Debye-Heckel linearization means when the theta potential value is very small compared to this ideal kind of configuration, and here we can get very straightforward analytical solution. Okay. Again, we have a steady unidirectional flow of low flow. This is a governing momentum equation. This is charge density due to electrical body force, electrical potential distribution, negative field body force, and in dimensionless form, we will be getting this kind of expression. Simple. What I have done, just represent, rho e value I have just replaced with this expression. And corresponding dimensional variables, Hartmann number, and with this ordinary differential equation with this complicated system. Okay. Now the question is, what do you think this equation is solvable to analytical method or numerical method? What do you want to use? Which method you want to use to solve this equation? Because anyway, this equation is already available with us. Solution is already in the solution. So which solution method you want to obtain? You want to use numerical or analytical? What do you think?
Numerical.
No. Analytical is possible.
Possible.
Yes. Show you. See this. Boundary condition and y sleep is already known. Maybe a sleep condition is y equal to 1. Top channel we have got a sleep. Sleep is basically no sleep means velocity is attached to the surface. No sleep means it can sleep. For example, sleep at the surface. You are adding some mass over the surface, it will create some sleep. So this is the sleep coefficient, we call it sleep coefficient. And this is the central line symmetry boundary condition. This is the analytical solution of the equation. So analytical solution is possible.
Sir, mathematical output just.
Mathematical output. Correct. It's not just, if you do it by hand, then you feel the pain. Just put this in online integrator, you will get this solution. So this is the parameters, but you should know the physics behind it. First time we should know. All of us should know. And these are basically called a hypergeometric function. So just see the mathematics books. What is hypergeometric function? You can get it. Hypergeometric function, and these are the values of different parameters present in this.
Sir, what function?
Hypergeometric function. Standard function like gamma function, beta function you already know. So this is a class of function called hypergeometric function. Okay. So now, what is the problem in this equation? Tell me. Equation has got some inherent problem. Solution you have already obtained, but what is the problem in this solution? Can you plot a velocity profile given the value of Hartmann number and y? MATLAB provide small code, you can plot it. But there is a problem in this equation. What is the problem? Hartman number is known, constant parameter. Y is also known, beta is also known, speed value you are giving. P is already known, then some function. P is also known function, R is also known. All these values are given here. Zeta is also your input parameter zeta. What is the value of E? Stream potential, is it known?
You said no.
How come?
From here.
From here, well, we have to calculate it.
E is already generated, sir. Potential.
How to calculate it? It is not known. It is function of velocity only. Is it known? Is it not known? Am I sounds is it reasonable? Is it known? It is not known, right? E is not known. E is a function of velocity because it is a action of velocity only. Steaming current will generate, conduction current will generate, current into strong current will generate. Then only you can calculate the steaming potential. That's why this E is not known here.
So we have to assume some function.
No, you can calculate it. As if you assume it, then it will not be a physical thing, right? If we assume it, so we have to calculate it. What is this is physical? Velocity is physical. Due to the velocity, the steaming potential is generated. So you have to calculate the steaming potential based on the velocity value.
And there should be a function.
Velocity value is a function of velocity, but velocity is of quality of 10. E is a function of velocity. Velocity value we do not know until unless velocity E is not known. That means E and E are coupled with each other. Now, how to calculate the value of E? We have to apply. We have to obtain the value of E. We have to apply this principle. It's called the inequality principle. How? I am showing you. See this. The principle states that in the absence of externally applied electric field, the induced electric field is developed such that the net current to the nano-conformity is zero. Nano-conformity is smart sensor to nano-channel. The net summation of all the currents is zero. Star layer, conduction current, star current, current, steaming current, conduction current, and current through the star layer. Summation of this, all these currents is zero. Now, these are the expression of steaming current, expression of conduction current, expression of current through the star layer from electrochemistry. Very simple. See, steaming current is a function of velocity. Conduction current only the charge, accumulation of charge, and this is current in the star layer. You add all those stuffs for I net equal to 0, you will be getting this expression. Correct? That means from here you can get E equal to Ui and dy this. You put the value of E, Q, and you can get the corresponding value of E. This is a coupled expression, and the solution is not possible. Here value of E, this integration cos alpha and dy can be done analytically, but U multiplied by this integration cannot be done analytically. You have to do some Trapezoidal rule or some method, numerical method you have to apply to obtain the corresponding integral value. Okay, so finally here you can get the value of E to satisfy this electronegativity condition. That means you have to obtain the value of E such that this electronegativity condition is satisfied. Okay, accordingly you can get the value of steaming potential. So once the steaming potential is obtained, you can correspondingly you can get the rest of the parameters. First parameter is that you have a thermally developing flow. Accordingly, we can obtain the thermally developing flow equation already we have obtained in the last case studies. And these are the different parameters. Temperature, duality parameter. You can see duality parameter has got some dependence. Sp equal to Sp into E square. E is basically steaming potential. In earlier case, we have got only Sp and some current conductivity dependence. But here only Sp equal to Sp into E square. This is the only important parameter. Duality due to steam potential development. This is one of our fundamental contribution in this area. That we have found out that Sp duality has got important implications when there is a steam potential development in a nano-channel. Again, what is the value of steam potential we can get? See that if we increase the zeta potential, steaming potential is increasing, it is reaching at a peak value, then it is going down. Why? The answer to this question is that as we increase the steam zeta value, bulk concentration of the ion inside the channel is increasing. As a result, steaming current will get increased. Because steaming current will get increased, steaming potential will get increased. Right? But at the same time, your conduction current will also get increased. If your bulk concentration of the ion is increasing by increasing zeta potential. So the competing consequences between these two, it will have a maximum value of zeta potential at a particular result location where steam potential value is maximum. Is it clear? Why we are getting this bell-shaped curve? Is it fine?
Sir, in the first case study, it was a symmetry along with the axis, but here unsymmetry. Why?
This is not the velocity, this is steaming potential.
Yes.
Yes. Why it is coming like this? Because if your zeta potential is increases, what will happen? Your ionic concentration inside the channel will increase. As a result of that, your steaming current will increase. If the steaming current is increases, what will happen? Your steaming potential will not increase. But at the same time, if your steaming current increases, your conduction current will also get increased. Then, as a result of that, there will be two competing consequences. Steaming current is increasing, conduction current is also increasing. So, as a competing consequence between these two, we will have a threshold value of zeta potential, where zeta potential value will, steam potential value will be maximum. After that, your conduction current is so high that it will create gradual decay of the steaming potential. Fine? Fair enough?
Yes.
Now, here also you can see if you increase the magnetic distance by increasing the value of parameter, we have a reduction in the steaming current because it is basically causing some motion, retarding motion, suppressing motion of the fluid flow, steaming current will get reduced. But at the same time, if you increase the speed value, speed parameter, if you have a speed in the flow, speed means basically it is accelerates the fluid motion. Suppose you have a channel which walls are basically substrate walls, you are using some wax. That is basically you are increasing the surface smoothness. Surface is becoming very smooth. The surface is becoming very smooth. What will happen? The fluid flow will be very fast. Right? Your no slip boundary condition or satisfaction no slip boundary condition will not be very much applicable there because surface is very smooth. Now, as a result of that, your velocity will definitely enhance. If the velocity is getting enhanced, your steaming current will also get enhanced. Your steaming potential will also get enhanced. Right? Here we have a value of steaming current with zeta potential for different value of parameter du, which is basically we call it Dukhin number. Dukhin was a scientist who given this value, number. This number basically is a manifestation of dominance of conduction current to Stern layer. So when Dukhin number is very high, conduction current to the Stern layer is very high. This Stern layer current is moving upwards. When Dukhin number is very small, conduction current to the Stern layer is very small. Now, if the Dukhin number is very high, you can see for increasing the Dukhin number, your steaming potential is get reduced. Because to satisfy the electric neutrality, where your steaming current and conduction current has to be minimum to obtain a constant value of electric neutrality or zero value of electric neutrality, so that accordingly this value of E will get reduced for increasing the Dukhin number. Is that clear? Any question? Okay? Again, we will the similar stuffs of velocity distribution. I am not going into detail because magnetic field suppress the fluid motion, velocity will get reduced, and your sleep also increase the fluid motion. You can see the effect of sleep for sleep parameter when consider sleep parameter velocity is increasing, right? Here no sleep condition, typical parabolic type of velocity profile. Who is sleep? This kind of velocity profile. Surface velocity is not zero at the walls.
Yes.
Temperature distribution, same more or less same. Thermally developing for different kind of Pictet number. Pictet number is a manifestation of flow velocity. If the flow velocity is very high, there will be a thinning of thermal boundary layer. If there is thinning now come to the very important parameter called Lucid number distribution. Here you can see Lucid number distribution. We have got some typical consequences. With Lucid number distribution, general data variation I have already explained in the last case studies. You can see that if you increasing this duality parameter, keep on increasing it, what is happening here? Lucid number is decreasing. Why? This is a very typical situation. If you increase the duality, temperature gradient in the wall is reduced. If the temperature gradient in the wall is reduced, your heat transfer will get reduced. Right? Now, that means SP effective, which is basically duality parameter, manifestation of duality parameter, which is basically SP into E square, that it is getting, if you increase it, your fluid will be more homogenized, your temperature gradient at the wall will reduce, your heat transfer will get reduced. That is basically manifested through this Nusselt number distribution. Now, what is your expectation? If a hard number, that means in the other way around, Joule heating parameter, if it is reduced, what will happen? Your temperature value will get up, temperature gradient will be very high, and heat transfer will be very high. That means Joule heating has got inverse proportionality with a Nusselt number. That means the Joule heating is very high, your Nusselt number will get reduced, heat transfer will get reduced. If Joule heating is very low, then your heat transfer will get enhanced, temperature gradient in the wall will get reduced. Fine? Here you can, and another thing is there, what is your expectation? If your negative field is very high, what is your expectation? If the magnetic field is very high, heat transfer will get up or get down? Fluid velocity will get reduced, will get suppressed. The fluid velocity gets suppressed, heat transfer from the wall to the fluid also definitely will get suppressed. Conductive heat transfer will get suppressed. Then it will decrease the Nusselt number. But what is happening here? You see, if you increase the Hartmann number, your heat transfer is increasing. This is a very important thing. That is our primary contribution in this area. We have found out that it is not only that the only applying heat transfer, Hartmann number, heat transfer will get reduced, but if you increase the Hartmann number, there is also possibility that heat transfer will also get enhanced. Why it is happening? We tried out, actually, we stuck out when we have this figure in our hand, really we got stuck. Then we explored many possibilities why it is happening. Then we found out that why it is happening is really interesting. This reason is fun. When we found out the reason, then it will give you some happiness, which you cannot compare with the happiness when you get lots of money. Effective Joule parameter, that we have seen that effective Joule parameter is something like this. That SP effective equal to SP into E square. Fine. What we have got? That as Hartmann number is increasing, E is also not increasing, it is decreasing. If we increase the Hartmann number, E will decrease. If E is decreasing, what will happen? SP effective? Decrease. It is Joule heating is getting decreased. If the Joule heating is getting decreased, heat transfer definitely decreased. Fine? Fair enough?
Yes.
Any question? We found out the reason that this is the case when just by applying the magnetic field, it is possible to increase the heat transfer when there is steaming potential in it. When there is in the absence of electric field, it is possible to obtain higher heat transfer if we increase the central magnetic field. Fine. So here you can see, if we increase the magnetic field, heat transfer also got increased. We got a initial critical comment from reviewer, but later on when we explored this, then it was accepted by the reviewing community. Yes, it is really happening. And my challenge to them is that definitely we can try this concept for development of smart sensors. Right? When there is a requirement, just in the absence of electric field, you can simply apply some magnetic field, high magnetic field, and some pressure field. It will generate some steaming potential force, and it will reduce the Joule heating effect, and heat transfer will get enhanced. That's why this study or this kind of analysis, if you can do this kind of analysis, it has got immense application for the design of smart sensors for heat transfer enhancement purposes. Okay. Again, we can do phenomenal analysis of entropy generation. Again, for any kind of design and other exercise, you require entropy generation analysis. So we have done some entropy generation analysis, so we have got similar kind of consequences. Fine? I have got only 10 minutes left, right?
Sorry, you continue.
I will continue. So somebody have findings, I'm just skipping. There is no point of now. So far we have considered the case where the fluid is Newtonian fluid. Fluid is Newtonian fluid. Now the question to you is that if the fluid is non-Newtonian, which is very much applicable for the mathematical application, synovial fluids, bloods, they basically show non-Newtonian characteristics. So they are the loss of Newtonian fluid that we generally consider for the macrochannel force is not applicable for the situation when the fluid is non-Newtonian. In general, bloods and other kind of fluids, basically they obey non-Newtonian behavior. For example, you know the Paul behavior of viscosity, Oswald-Welle model, and also there are Maxwell models. There are several models available. So, in general, for example, if you apply or if you use Paul kind of model for calculating the viscosity of a Paul fluid, so that Paul n equal to, so when n equal to 1.3, it is the manifestation of a blood. So you can basically characterize the blood flow just by using this Paul model of viscosity. It is also possible. Now the question is that we want to study the same situation when you can see the extensions that we can do this kind of research work. You can do the similar kind of extensions. A to method have an EMH flow when the fluid is non-Newtonian fluid, when the fluid is blood or those kind of situations. So here what we have considered that instead of thermally developing flow, we consider thermally developed flow. That temperature is already developed. There is no point of thermally developing. But here there is a only fluid flow in the absence of any electrical body force. Only fluid flow, magnetic fluids applying in the perpendicular direction, and as a result there will be generation of steaming potential. So we want to determine that what is the value of steaming potential we are getting for this kind of flow for different kind of Paul fluids. Basically, use the manifestation of blood or certain kind of stuff. And when we apply here, please note that here we have not considered the cases for temperature, constant temperature boundary condition. Rather, we have considered when the walls are maintained at a constant heat flux. So under this situation, we would like to analyze the corresponding flow through macrochannel, or we can design some sensors. We can design the output of a sensor which can be matched with the experimental results for the situation when the fluid is a viscously elastic fluid or Paul fluid. Okay? So this is the situation. Here you can see this is the center line. And we have put our axis at the bottom of the channel, y-axis. So let us see what is the consequences. Again, conventional. So whether the fluid is non-Newtonian or the fluid is Newtonian does not matter. Ideal potential will be as it is. Okay? So I was explaining in a first part of our lecture that ideal potential has got some dependence of the pH of the solution. This is a typical expression through which one can approximately determine the value of ideal potential for the given value of pH and given kind of ionic activity. This is the expression which is widely used by scientific communities to obtain the value of ideal potential for different kind of parameters. And it is surface charge density sigma. You can see if you want to solve this equation, you require the value of ideal potential and also the state parameter value. Here this equation, if you just integrate it once, we will get this kind of expression. Just simple small integration, and these are the different parameters for dimensionless parameter. Now this equation requires value of ideal potential, but here we are not specifying the ideal potential a priority. What are we getting? We are just determining the value of ideal potential for a specific value of parameters that we have considered here. So let us say for pH equal to 5. pK value, which is value available for viscoelastic fluids, and say for different Kb, T, electronic charge, we can calculate the value of ideal potential. And ideal potential is depending with the surface charge density, which can calculate ideal potential here. You can put it here. You can obtain the value of steam potential. This is an iterative process, and this requires simultaneous iterations. Now, for non-Newtonian fluid, what is the difference between the conventional Newtonian equation, Navier-Stokes equation, and non-Newtonian equation? It has got some stress tension term, and a body force term. So, body force term basically this stress tension term we assume a power law behavior, power law simple power law model we have considered, and basically if we introduce all those stuffs here. With the magnetic field also, this is AB is the magnetic field already you know, Hartmann number square into U and those parts. If we apply here, if we substitute all those stuffs in this equation, you will be obtaining this governing equation for the power law of fluid. That means when the fluid is flowing through the macrochannel, and if the fluid is non-Newtonian fluid, you will be getting this kind of equation, power law of fluid flow equation to the macrochannel. Okay. And m is the power law index and phi is the flow consistency index. Already you know this stuff. Very simple stuff. Book is from book actually. And then E is the steaming potential. E the energy of potential. And this part already know. Again, E is unknown here. Now you may ask me, can you solve this equation analytically? Answer is no. This equation cannot be solved analytically. You require numerical method. Can you use numerical method available in MATLAB? Answer is no. You have to use some standard numerical method called TDMA. Already you know tridimensional matrix algorithm. Some of you may know. It is very simple. Just you can Google it or you can get from Wikipedia resources. The tridimensional matrix algorithm you use method you can simply apply and you can get the solution, numerical solution of this problem. U. Once the U is obtained, you have to obtain the value of E, which can be obtained through this inequality considerations. Okay? Because here E is unknown, when E is known, U is known, and U has to be substituted in this expression to obtain this value of E. It is not so straightforward. It requires some advanced numerical techniques because this equation and this equation they are coupled. Because U has to be obtained iteratively through numerical method TDMA, and that you have to value of U has to be substituted in this equation to obtain the value of E. This is a coupled equation. Now here basically we have used TDMA method and coupled with standard iterative technique. So there this you can apply. So you can get this solution. Again, thermal energy equation, because you want to basically just tell me why we require thermal energy equation when we are considering this non-Newtonian kind of flow. Because you know when you are thinking of say lab on a CD application, in a CD we have got some device inside the CD and the CD is attached with different mapper channels, and different mapper channels we have a different sources. We are putting our blood and we are applying some magnetic field to blood to flow the mapper channel and go into the reservoir. Now while going through, due to the action of physical dissipation, it may experience some heat generation. You have to minimize the heat generation because if heat generation is very high, what will happen? Your particular samples may get damaged. That's why you require this kind of analysis with the consideration of temperature distribution. How I develop kind of flow? Because here, if you know how much magnetic field you have to apply when the heat generation is minimum, that kind of magnetic field you should require for design of lab and seed kind of devices. But the fluid is not need blood or synovial fluid, saliva, this kind of stuff. So here we have considered standard thermal development flow consideration, and also these are the thermally developing flow uniform wall heat flux, standard book, standard textbook material, incorporate heat transfer book. Just find it, you can get all this stuff. And finally, just energy balance you will be getting finally this kind of expression for dimensionless energy temperature distribution equation with bulk temperature and Knudsen number value, and the boundary condition is that at y equal to 0 at the y equal to 0 at y equal to 1 theta greater than this equation is not possible to solve analytically. You have to apply numerical method. So here also we have applied TDMA numerical method to obtain solution of the numerical temperature distribution. This is the typical solution for the velocity distribution. How the velocity value is varying for different power law index. So when m is equal to 1, the fluid flow corresponds to Newtonian fluid flow. When m is less than 1, we call shear thinning fluid flow. And when m is greater than 1, we call shear thickening fluid flow. Shear thickening fluid like paints, this honey. Okay, shear thinning. You can call it spirits and all the stuff called shear thinning fluids. You can see this when the value of m is increasing. It's not clearly visible properly here. I don't know that your shear thickening effect is taking place and velocity gradient is also increasing. At the top, you have peak velocity, then it is getting reduced. The value of region is getting reduced. The typical characteristics of non-Newtonian fluid. And also here we apply magnetic field. It is also showing the similar kind of characteristics. They apply magnetic field. Your velocity is getting suppressed. Now also velocity is getting suppressed. Steam potential development. Here you can see we have applied the different value of m. For different value of m, how the steaming potential is varying with the magnetic field. In general, if we apply the magnetic field, flow velocity is getting suppressed. your streaming current will get reduced, your streaming potential will also reduce. But at the same time, if we increase your power law index, for example, shear thickening fluid at m equal to 1.5, you have a more streaming potential than compared to the m equal to 0.6. Why? Because m equal to 1.56, you have a peak kind of velocity distribution, right? You can see this peak velocity gradient. So peak velocity gradient is coming. That's why streaming current is very high. You are streaming potential distribution. Okay? And also Dukhin number already we know that in the Dukhin number case, their streaming potential will get reduced because current will go in an alternative less resistant path. This is the result temperature distribution for different kind of temperature profiles. Also, you can see temperature profile usually consequences of velocity. Higher velocity means higher temperature, and vice versa. Please one. Have a look. Here. Number is decreasing with the increase in velocity. It was and also duality parameter already we have explained. Increasing duality parameter, you have a decrease in heat transfer because it increases the wall temperature, reduces the wall temperature gradient. That's why heat transfer is decreased. Entropy generation part already you know. I've already similar kind of because in all the studies we have done a phenomenon analysis of entropy generation just to give a flavor that if you can do some entropy generation optimization, which can be used by the industry to devise this kind of smart sensors for biological and biomedical applications. Okay. I have got another thing, but I am not going into details because just what I have done, instead of non-Newtonian fluid, I have used PTT fluid, pan-thinner fluid. So complete analysis is theoretical, analytical, no numerical part in it. So this paper is my single paper. Physically, it was published in 2020. So here actually just go to this paper, you get all the information. I just am giving one flavor. This is a typical macro channel where the fluid is, instead of power law fluid, I have used non-Newtonian PTT model, which is a very complicated model in terms of because it has got complications because it is it has got some more standard tensor dependencies for different values of input parameters. That's why and also it mimics a typical situation of synovial fluid, saliva. So this kind of situation, so with PTT model you can also model it. I'm not going to detail because PTT model here I am going to show you. This is the momentum equation you will be getting for the PTT model. This is the momentum equation, velocity equation. Here Wi is a Weissenstein number, which is basically the description of your shear thinning characteristics. Wi is very high, your fluid is more shear thinning. Wi is very less, equal shear thickening, equal Weissenstein number. So here, this is the analytical solution we have got. This is the solution for velocity. Complete analysis is analytical. So you can see to the analytical analysis, you just put all the values and you can obtain the solution. Li is the polynomial functions. And theta potential. Here again the problem is E is not known. Again E has to obtain through electronegativity principle. Summation of all the currents together. And again also we have also calculated the energy conversion efficiency. Energy conversion efficiency means how much electric voltage you will be getting for a given flow rate. That is the manifestation of energy conversion efficiency. We have found that for different values of power law index, different values of Weissenstein numbers, it is possible to obtain a giant energy conversion. So you can get a very high value of energy conversions. Similarly, flow rate you can simply integrate it and you can get. Also, you can get all the stresses, normal stresses and shear stresses. This is standard expression of stresses, and also the shear viscosity. This velocity profile already is fine. You can see this. I am going to show you some typical analysis here. You can see that the variation of streaming potential with theta potential is universal. That is the main point I want to stress here. That for all the cases, whether it is a non-Newtonian fluid, whether it is a PTT fluid, does not matter. This variation is universal. If you change the zeta potential, you are bound to get this kind of variation for steaming potential. So for industrial application, for smart sensor applications, if you have the zeta potential variation, you will get this kind of steam potential variation. That's one matter. Here also with Eisenberg number, that is basically manifestation of shear thinning parameter. So you will get more shear thinning characteristics for increasing the Eisenberg number. That means you will get peak velocity profile at the top. So you will be getting high steam potential. Flow rate also has one similar resemblance with the steaming potential. And shear stress also, you can see at the wall shear stress is definitely high. As we go towards the center line of the channel, the shear stress will get minimized. Viscosity also has one similar thing, and the center line, your gradient is slow. Effective viscosity is very high. As we go towards the wall, velocity gradient is increasing, viscosity will get reduced. This is the standard expression. Energy conversion efficiency. How much energy output, how much steam potential output you are getting for given value of flow rate. So you can see energy conversion efficiency also following the typical profile of steaming potential. So that means your steam potential is very high, you are bound to get high energy conversion efficiency. This is the final conclusion of this study, because from this you can basically devise your smart sensor, or you can design your smart sensor. You can see for typical value of beta potential, typical value of Eisenberg number, which is manifestation of shear thinning characteristics of PTT fluid, you are bound to get very high flow rate in this region. Similarly, here also you are bound to get very high flow rate in this region for a particular value of beta potential and Eisenberg number. This is the typical characteristics. This is some of the references. This is my actually when I joined Jadavpur University, so I got some sponsorship of ACRP and I got a grant there, and I developed this laboratory, which I named it Mathematics Laboratory, ACRP sponsored Mathematics Laboratories. You can see they are different. These are member channels actually. These are member channels. You can see member channels and some facilities we have developed. So here actually we have done some analysis on path selection of bubble model. So if you know the typical characteristics of a bubble at the inlet for a complicated bubble network, so and if you have two bubbles, so where the second bubble will go, you can predict a priority. So this paper is done by a student. Now he is doing PhD. During his MTech actually he did his work and is published in Peaks of Physics. Here also we have done some research work here. Here we have done that you see if you have an artery and there is a cholesterol build-up in the artery, so you have this kind of corrugated network, corrugated kind of channel. So channel you have a lot of corrugations. If there are a lot of corrugations, now what will happen? How the bubble movement will affect? We can actually predict through numerical modeling and also some experimentation. So we have done numerical modeling here with my PhD students. The paper is under Physical Fluids Journal, so will not record any report here. So you can show you some animation and you can see how the bubble movement will progress for different capillary number. This is for low capillary number. Bubble is moving. Low capillary number you can see. Capillary number is a manifestation of your surface tension. Capillary number is low, surface tension is very high, and vice versa. See how it is getting changing for low capillary number. Now if you have a medium range capillary number, you will be getting this kind of propagation, bubble propagation. How the bubble is getting propagated for medium range capillary number 0.19. So you can see portlet shaped bubble, capsule shaped bubble, this kind of bubble is going to get. And for a high capillary number, you can get this kind of propagation. This capsule shaped bubble. These are the things you can get. The bubble is moving inside an upper channel, corrugated upper channel. We are planning to do some experiments and for this study. We are expecting some grants from ACRP. If we get it, we will participate in this. We are. Thank you for this one. Thank you very much.
Thank you, Professor Shankar, for your very engaging and interesting deliberation. Now the floor is open for question. If you have any question and you ready, please shoot us. Any question?
Actually, we have already interacted with the participants. So you may ask any questions.
So if there is no further question, I have some questions.
Please.
So first of all, in the study that you have shown that entropy analysis for considering the optimization of the heating effect, is the standard procedure or you are proposing it?
No, it's standard procedure.
It's standard procedure.
Yes. And for the number channel aspect, we are the one who have introduced this analysis for the number channel analysis. It's the first, one of the first kind of analysis we have done.
Secondly is you have considered this biological fluid flow. And biological fluid flow, some of the fluids like synovial fluid, they may show some time variant behavior. Did you consider that?
We have not considered. That may introduce complexities in the flow. It's a very good question actually. So you can also consider. In that case, you may get some deviation in the result, but more or less, average property will be the same. Average velocity variation, average flow rate will be the same. Localized change you may get.
And when we talk about microfluidic channel, conventionally, what we think of it is what you have shown. Okay, even if you are using the biological sample, what you are showing is that we have taken the biological sample out of the body in vitro, and we are doing some analysis for that. We have to maintain some conditions so that they don't denaturate.
Correct.
So, but in our body, in vivo also, there are different microcellular flows, and understanding them will give different very good physiological cues for treatment. So, did you consider, are you aware of any such study?
You can also, because in that case, there are two ways of studying those analysis. Either you can perform experiments, that is also very difficult, but you can perform theoretical analysis. So generally people, so there are many scientists, they have done those kind of analysis. They use archetype coordinate system. So archetype coordinate system, you can perform those analysis. But at the same time, what are the analysis I have shown here, same analysis you can implement in those studies and you can get a similar kind of results.
So, okay. So, one more question, sir. In the last slide, the last experiment you were showing is bubble movement. Physiologically, what these bubbles are?
That means in the...
Say you are talking about artery. Bubbles of what? I mean, in the artery, there will be blood flow, right?
Correct. In the artery, there will be blood flow. Bubbles you can consider...
There not be any air bubble. And if there is air bubble, it may cause some problem.
It may cause some problem. At the same time, you can consider drug, basically, drug particles.
Okay.
Bubble you can substitute, you can manifest the bubbles concentration as the drug particles. You can have the different kind of fluid properties.
It can be dispersed solid particles inside the fluid. That's what
you can also consider dispersed. But here you can
more
dispersed
bubbles are kind of deformed.
Yeah, more dispersed bubble you have considered. Polydispersed also you have considered, but in that case, this macrofluidics analysis for dispersed bubbles it requires some external field in terms of electrical molecules. There are studies I've done recently.
And you have considered this corrugated shape. So, when they have said that you have communicated the paper, I'm not sure, you will answer that. So, basically, when you are doing a theoretical study, and you are doing a theoretical study based on certain things, say which is exist in the human body.
Correct.
So there may be a need for validation of that, whether such pattern is already present. So
correct.
Yes.
The University of New York Stony Brook recently last year they have done similar kind of analysis experimentally. So we have mimicked their analysis for the numerical analysis.
So
we have validated our result with the experimental result already published by Sawyer and that.
Okay. So what is the process of the experiment? What kind of instrument do you have?
I don't have exact idea. So basically, they have manufactured macrochannel this kind of corrugated shape.
Kind of angiography kind of thing that will move through the capillary.
Something like that. So that paper is Digital Review Journal paper is there. So they did some experiments.
Sir, one more last question.
Please.
Sir, you have, in my opinion, very fantastic analysis just using MATLAB, which is not a specialized or dedicated, I will say, software. But what you are analyzing is multi-physics flow. So, you have shown one case that which may not be possible to solve alone using MATLAB. So in those cases, do you recommend commercial software like Console, or do you write your own code? And what is the justification?
Good question. So for example, one-dimensional kind of flow, two-dimensional situation. So you can use MATLAB and get the solution, analytical solution, numerical solution. Yeah. We have a two-dimensional, three-dimensional flow. So there I would recommend Console. Yes.
So
and is also good. Console is for research purpose. Console is more superior than ANSYS. Yeah.
Okay.
I also use console.
Okay, you don't write your own code or?
Yes, actually, one of my research area is also fluid structure interaction, FSI.
Right.
So recently I have got one publication in German fluid mechanics. You can also see. So basically, what I did actually, there is a plate which is basically fluctuating in this motion.
Okay.
So I have a collaborator ID Guwahati, so we jointly work and basically also do it.
So basically some ghost nodes and that are moving back.
Correct, absolutely correct. Yes, what it was now.
Thank you.
Very good question.
Okay, so thank you once again, Professor Sharkar. We are at the end of this very interesting session. So now in the second half we have two different plans. For persons who are attending FDP, we will have an industrial visit. So after lunch,